Yeah, very good morning once again. So today we are going to start our lab experiment. So in the previous classes, we studied about the basic instruments. We studied how to handle a vernier caliper to measure the thickness, to measure the breadth, and to measure the depth. And also we studied about screw gauge. With the help of a screw gauge, we came to know how to measure the diameter as well as the thickness of the given material. Today we are going to start our experiment. The experiment number 1 is Torsion pendulum. So this Torsion pendulum comes under modulus of elasticity. Here the modulus is rigidity modulus. So we have to learn first what is mean by modulus, what is elasticity, and what are the types of the modulus. Today we are not going to start our experiment, but before going to our experimental part, we are going to learn some basics about the modulus of elasticity. So let's start our class. Here, the Torsion pendulum is used to measure the rigidity modulus of the given wire. So we are going to measure the rigidity modulus. The rigidity modulus is measured for the given wire. We are going to use a wire in our lab. So for the wire, we have to measure the rigidity modulus. So later we see the procedure how to measure the rigidity modulus of the given wire. But here we are talking about the modulus of elasticity. Modulus of elasticity. So we know what is elasticity. Elasticity is nothing but when we apply the force, to the material property changes. When we remove the force, then the material regain to its original condition. It's called elasticity. For example, consider a rubber band. When you apply the pressure over the rubber band, that is when you apply the outward pressure in the rubber band, we know that the length of the rubber band will expand. When you remove the pressure, the rubber band comes to its original position. It's called elasticity. So when the material regains to its original position, even after the removal of the external force, when the material regains to its original position. So regain to its original position means we are applying the force on the rubber band. When we remove the force, the material regain to its original position, come back to its original position. That's only we are saying as an elasticity. When the material regain to its original position, even after the removal of the external source. The external source, removal of the external source. The removal of the external source is nothing but what pressure you have applied on the rubber band. When you remove the pressure, it will come back to its original condition. When the medium return back to its original condition, even after the removal of the external source, force or pressure, such type of medium are called as elastic medium. So this is the elasticity. Then what is mean by plasticity, sir? plasticity is opposite to the elasticity. When the material does not regain to its original condition when the external force is removed. How to learn this? Again, consider a rubber band. Apply the force on the rubber band. Give the external force on the rubber band, on the two ends of the rubber band with the help of your hands. As we know that when we apply the pressure, when we apply the external force continuously, the elasticity reaches the critical limit. The elasticity reaches the critical limit. That critical limit is nothing but maximum position up to which the material behaves as an elastic material. We know that. We did it. We practiced many times. So by occasionally, with the help of the rubber band, we played this concept. We apply the pressure externally on the rubber band. At one stage, we all know that the rubber band elasticity lost. The rubber band elasticity will diminishes. Then automatically what happened? The length of the rubber band will increase. The material does not come back to its original condition. So when the material does not able to come back to its original condition, then such type of material are called as plastic material. So a better example for to learn the elasticity and the plasticity is you have to consider the rubber band. When we expand the rubber band, it will elongate. When we remove the pressure, force, it will come back to the original condition. When we again expand the rubber band, it will increase. It will increasing. It will go up to some certain limit. Beyond that limit, when you apply the external pressure, the material property diminishes, completely changes. It does not regain to its original condition. It's called elasticity and it's called plasticity. Here, I have shown the modulus of elasticity is nothing but stress by strain. So generally, the modulus is defined as stress by strain. What is this, sir? Stress by strain. We all learned about the Hooke's law. We all know about the Hooke's law. Within the elastic limit is nothing but the maximum point. Is nothing but the critical point up to which the material behaves its elastic property. It's called as within the elastic limit, the stress is directly proportional to the strain. When we apply the stress over the material, the strain will be takes place. How we come to know this? The stress is nothing but force on the unit area. If suppose in front of you, one boy is standing or one girl is standing, when you apply the pressure on that boy or a girl, what happens? She or he go away from that position. So when we apply the force on the body is nothing but in a unit area. When we apply the force on the unit area, it's called stress. Stress is directly proportional to the strain. What is strain? Strain is nothing but initially the person is standing in one position. When we apply the force on him, definitely he will go somewhere. So its position changes. Its position deforms. That deformation, that change is nothing but called as the strain. So stress means force on the unit area. Force on the unit area is called stress. Strain means change in dimension. Change in dimension. Dimension means length changes takes place. Volume changes takes place. Angular changes takes place. So we can study this modulus in three ways. That is linear wise changes. We are going to study in Young's modulus. Angular changes. We are going to study in rigidity modulus. Volume wise changes. We are going to study in the bulk modulus. So these the three modulus of elasticity. So here you can able to see the modulus of elasticity consisting of three types: Young's modulus, rigidity modulus, bulk modulus. If someone asks you what is mean by Young's modulus, see Young's modulus, you can split these words into two. Young's one half, modulus another half. In three types of these modulus of elasticity, we are having the term modulus common. So the modulus means stress by strain. Modulus means stress by strain. If you are going to define about the Young's modulus, so what you have to do, Young's means linear changes. You have to know this. Young's means linear changes. Linear is nothing but lengthwise changes. Lengthwise changes, if a change is happening, then it's called as Young's modulus. So length is nothing but a Young's modulus, stress by strain. So we can write that linear stress divided by linear strain is the Young's modulus. The Young's modulus definition is linear. Linear is nothing but a lengthwise. That's why we are using the word linear. Modulus means stress by strain. So we can modify the modulus into Young's modulus as linear stress divided by linear strain. Or we can write as length stress divided by length strain. Length is also an exact term. Instead of linear, we can use the word length also, because we are studying the lengthwise changes. So the length is here called as the linear. So linear stress by linear strain is the Young's modulus. Rigidity modulus. Rigidity means angular changes. Angular changes. So for rigidity modulus, how we have to write the definition? Angular stress by angular strain. That's all. Angular stress by angular strain is the rigidity modulus. What about the bulk modulus? Bulk modulus. Bulk means volumetric changes. The change in the volume. So the volumetric stress by volumetric strain. Volumetric stress by volumetric strain is the bulk modulus. So this is the introduction for modulus of elasticity. Why, sir? Why you are considering this modulus of elasticity here in torsion pendulum? So you can able to see here the objective aim. It is used to determine the rigidity modulus of the given wire. Rigidity modulus of the given wire. So we are going to measure the rigidity modulus. Rigidity means angular changes, angle change, angular change, angle wise change. So the angular stress by angular strain is called the rigidity modulus. So this is the small introduction about the torsion pendulum. Okay. So I informed that modulus is defined as stress by strain. So here you can see that what is stress? Stress is equal to force by area. Stress is equal to force by area. See here, we are having a just a material in the form of a rod. So first you can able to see the total length of the material is L0. The first you can able to see the total length of the material is L0. So this L0, the length material is nothing but an original material. Without any force is applied over this material. We are simply taken the material and we placed the material in the stand. It's called the original length. It's called the original length. On the other side, we can able to see that we are applying the forces at the ends. We are applying the forces at the ends. So here in the left hand side, we are applying the outward force, and similarly in the right hand side we are again applying the outward force. So when we apply this outward force, we know the length of the material changes. The change in the length here, it's mentioned as del L. It's mentioned as del L. So the strain is defined as change in length. Change in length is nothing but a del L to the original length. Here the original length here considered as L. Actually it's not L, it's L naught. So del L by L naught is the strain. So when we apply the stress over the material, then only we can able to get the strain. When the stress is not applied to the material, the strain will not be takes place, because the stress is directly proportional to the strain. This is the Hooke's assumption. According to Hooke's law, he defined that within the elastic limit, the stress is directly proportional to the strain. So when we apply the force on this unit area, this end is in a unit area. When we apply the force on the unit area on both the side, it's nothing but a stress. When you apply the stress, then a strain will be takes place. The strain is nothing but change in length to its original length. We can able to see here what will be the original length and what will be the change after applying the force. So this is called the modulus. So the modulus means stress by strain. Stress means force by area. Strain means change in length to its original length. So how we are just measuring these changes? For that we have taken this example. Original length L naught. After applying the force on the unit area, it becomes del L or IL. So I have taken a small picture here to explain the concept. See here, we can able to see one person, one object, one boy or a girl standing in the rod. So one end of the rod is a fixed and another end of the rod is seems to be a free one. So when the person is not placed here in the rod, we can able to see that the length of the rod is a linear. The length of the rod is seems to be a linear. That I have mentioned as the original length. That I have mentioned as the original length. So after this original length is measured, then the person is standing at the end of this rod. End of this rod. So we can able to see that when the person here standing at the end of the rod tends to bend. The rod tends to bend. So this bend is nothing but a changes. The bend is nothing but a changes. So the force is applied on the unit area. The force is applied on the unit area. The force by unit area is nothing but a stress. When we apply the stress, automatically what happens? Linearly placed material converted into bending material. So this bend is nothing but change in the length. So we know what is strain. Change in length to its original length. So this is a small image I have taken to explain this concept. When the one end of the rod is a fixed, when the another end is seems to be in a free end, so this is nothing but called as cantilever. It's called as cantilever. Why, sir? Why we are calling this as a cantilever? The principle of the cantilever is one end of the medium is a fixed, another end is seems to be in a free end. So before applying the force or before placing the object, it will be looks linear. When we apply the force, we can able to see that the material tends to bend. The material is bending here, but the material is not break. The material is bending here, we can able to see that, but the material is not broken. So it means that, so this is happened within the elastic limit. If suppose the person is coming out from this end to the launched place, to this surface, so we know that the rod come back to its original position. Just an example we have shown here. So practically we are seeing this in the swimming pool. So just for driving, we are just seeing this one. The swimmers, they used to drive from some limit inside the water. So at the time they will go to the corner only. When they move to the corner, we can able to see that the end will makes to vibrate. So they will apply the just a force on the end. That end is nothing but a unit area. It's called as the stress. So when they apply the stress, we know that automatically the rod will tends to vibrate down and up, down and up. That is nothing but a strain. At one stage, what happens? They will get down. When they will get down, the material regain to its original condition. If the material come back to its original condition, then it's called as an elastic material. Suppose if the material is not able to come back to its original condition due to the force which we applied here, so then it's called as a plastic material. So these are changes. So the three types of the modulus of elasticity: Young's modulus, bulk modulus, rigidity modulus. The rigidity modulus can also be called as shear modulus. Shear is nothing but a change in the angle. So the Young's modulus means change in shape and size. Shape and the size both will change in the Young's modulus. In bulk modulus, the change in size but not in shape. Size only changes but not its shape. For the rigidity modulus, change in shape but not size. So size remain unchanged, but the shape will changes. So these are all the difference between these three types of modulus. Linear modulus means change in the shape and size, both will change. Bulk modulus means change in size but not shape. Rigidity modulus means change in shape but not size. So these are just an example for these three types of the modulus. See, we are applying the force. The arrow mark is nothing but the force. For the Young's modulus, I am applying the force in the downward direction. So we have to imagine that this upper end is fixed. The upper end of the rod is fixed. The lower end is subjected to some load. When we apply the load at the lower, we can able to see the deformation changes. The length will change. The length will change. Then second one is the rigidity modulus. So these our consideration. This only we are going to study in our laboratory classes. We are going to measure only the rigidity modulus. We are going to measure the shear modulus by torsion pendulum method. So what is torsion pendulum method? How we are going to measure the angular changes, that we can see later. But now the basic principle. The modulus, shear modulus. So here the object which we have shown here in the just a rectangle slab, it seems to be a stationary one. So for this modulus, I am applying the force of the surface. So we have to imagine that the bottom surface is fixed. The bottom surface of this modulus is fixed. On the top, we are applying the force. When we apply the force at the top, when the bottom is fixed, we can able to see that the medium slightly changes. So medium changes. So there will not be change in the shape. Shape will remain the same, but the size only changes. The size only changes. See here, the dotted line. The dotted line shows that the angular changes. So how much the medium is deformed, how much the medium is tilted, how much the medium is rotated. So that rotation, that change, shear, that tilt, it's measured by this position. Dotted line is the change in position. The straight line is the original position. So in between we are having in a smaller region, That a region is nothing but the shear. It's nothing but an angle. That angle is nothing but an theta. So this for the second one. Bulk modulus. See here in the bulk modulus, we can able to see that we are applying the force in all the directions. We are not applying the force in one particular direction, but we are applying the force in all the directions. The material is in a cube. Let imagine we have taken a rubber cube. Rubber cube. When we apply the equal number of forces, not an unequal force, equal force. So the same equal force is applied on all the sides of the cube, rubber cube. So we can able to see that the deformation, the shape changes. So the size will changes. The size will reduce. The shape will not be changed. So this is the bulk modulus. So this is a difference. Young's modulus means we have to apply length linear wise. Whether the medium is placed in vertical manner or whether the medium is placed in the horizontal manner. So we have to first initiate the position, which position we have placed the material. If it's placed horizontal means we have to imagine that if it's placed horizontal means we have to imagine that the medium is placed without any initial forces. So we have to apply the force on both the ends. Then we have to make the medium to elongate. If the medium is placed in the vertical way, so the vertical way is nothing but one end of the medium is fixed already. Already is fixed with some force. Through the another end only we are separating the external energy. So it's called vertical force. So here in this shear, the medium is fixed. We are applying the force only at the top, only at the surface. By applying the force at the surface only, we can able to see that an angular changes will be takes place on the material. In the bulk modulus, we are applying the force on all the sides, not on the particular side, but the force is applied on all the sides. When we apply the force on all the sides of this material, we can able to see the material due to this pressure, they change in the size. So this is the bulk modulus. So our consideration, rigidity modulus, what we are experimentally going to do. How we are going to measure this rigidity modulus, angular changes. To measure these rigidity modulus, angular changes, the basic apparatus, we have to consider the metal chuck. The metal chuck is just which was fixed at the wall. We are going to fix this metal chuck at the wall. So here we can able to see the just end, tip end, pencil tip end. So here in this pencil tip end, we are going to join the long wire. It may be in a copper wire or an aluminum wire. So it depends on the examiner and it depends on the aim. So we are going to consider the copper or a brass wire here at the tip. So the one end of the wire is going to be fixed by the chuck, and here the another end of the wire is again connected to the chuck, and then through the chuck it connected to the metal disc. We are going to connect to the metal disc. So when there is no any changes, there will be no changes in the length of the wire. It means that when the disc and the wire is remained stationary, when the force is not applied to these two medium, then there will be no any deformation. The twist, the rotation is not takes place. So what we are going to do, we are going to so the metal disc is rotated with respect to some symmetric masses, equal masses. So I am going to consider 50-50 grams of the mass. So I am going to place this 50-50 grams of the equal mass very near to these chuck. It's called a D1. when the metal mass, when it placed near to this metal disc, the distance is considered as d1. So what we have to do, we have to place the symmetric masses near to these center rotating metal disc, and we have to measure the distance. After measuring the distance, then you have to measure the length also. So from this point to this point, from this pencil end to this pencil end, we have to measure the total length. For example, if you asked to fix 50 centimeter, so what you have to do, you have to adjust this bottom disc, and you have to increase the disc position in the upward direction. With the help of the meter scale, you have to fix the position to 50 centimeter. Then you have to seal it, close it tightly with the help of the screw. After that, place the mass M1, M2 or M very close to the metal chuck at the center. Then rotate the metal disc. So when we rotate the metal disc, as we know that the one end of the disc is highly fixed, another end is connected to the disc. We are applying the force or the pressure to the disc, so the wire tends to twist. The wire tends to twist because the one end is fixed. That twisting of the wire, it's called the rigidity modulus. The twisting of the wire, it's called rigidity modulus. That only we have mentioned at the last. See here we can able to see the arrow mark which was mentioned in the red color. The arrow mark is rotating on both the sides. It shows that when it starts to oscillate, then the twist in the wire takes place. The twisting couple will be takes place. That a twisting couple, it's mentioned here in B. We can able to see that region, the small region. The small region is nothing but a twist. Later, this end with the original end, the opposite end with the change in the length. It's nothing but after rotating the wire twist. That difference here is measured as a theta. The difference here is measured as a theta. So this is a way we are going to measure the rigidity modulus of the wire. So the one end is a fixer, another end is a metal attached to the metal disc. Taking a equal symmetric mass, we are going to place the symmetric mass very close to each other, and we are going to fix the length for 50 centimeter length. Then start rotating the metal disc by considering any one metal mass as the reference, because we have to measure the to and fro oscillation, one complete oscillation. So the one complete oscillation is nothing but if you are going to start from here, it will go like this, and then it has to come back to its original position. Then it called one oscillation. Like that, we have to measure continuously for 10 oscillation, and we have to measure the changes with the help of the stopwatch. The stopwatch is a basic one. By this, we are going to measure. Just a minute. Sorry for the interruption. So this is the way actually we have to measure the readings. So the one end of the medium is a fixer. Through the another end, we are attaching the metal disc. We have to fix the length. So here in the metal disc, we have to place two symmetric masses, equal weight. 100 grams means both will be the 100 grams. 50 grams means both will be the 50 grams. So the equal symmetric masses to be placed near, and it should be placed at the farther distance. Then you have to start rotation. For a complete 10 oscillation, we have to measure the readings. So this is the procedure for the rigidity modulus. So this is the formula for the rigidity modulus. 8 pi I naught L by a power 4 t square. So the 8 pi is a constant. L naught is nothing but a moment of inertia. So the moment of inertia is going to be calculated with the formula mr square by 2. L is the length. We are going to vary the length of the wire. 50 centimeter, 55 centimeter, 60 centimeter. Like this, we are going to vary the length. T is the time period. So for a 50 centimeter length, for a 10 oscillation, what the time that we have to measure? These are, sorry, the A is the radius of the wire in meter. So with the help of the screw gauge, we have learned the screw gauge principle. With the help of the screw gauge, we are going to measure the radius. So the moment of inertia I naught, for that we are having a separate formula. M is the mass of the disc. So we have to know the total weight of this disc. And R is the radius of the disc in meter. So radius of the disc in meter. With the help of the thread also, we can measure the total radius of this disc. So this is the procedure. Now we are not going to start the experiment. So I want to explain some of the basics that I have started. In the next class, we are going to see what is meant by the rigidity modulus by using Torsion pendulum. Now I wish to share some videos relevant to this concept. Let's see. After that, if you have a doubt, we can clarify our doubt. Is it clear?
Yes, sir.
Yeah, Maya. I will play some video, just you see that video. After that, we can start our process.
When we hear the word elasticity, the first picture that comes to our mind is something like this. But is this really what elastic means? We will find that out in this video. Let's take an example of a helical spring. When a force of compression or tension is applied, the helical spring gets deformed, that is, it changes in shape or size. This force is referred to as the deforming force. And the ability of an object to regain its original shape when the influence of this deforming force is removed is called elasticity. More examples of such objects include sponge balls and rubber bands. When compressed or stretched, they get deformed, but they soon return to their original shapes. This self-reversing deformity the object goes through when forces are applied and removed is called elastic deformation. But is there a limit to the elasticity of an object? Do elastic objects remain elastic forever? Not really. For instance, if a great amount of force is applied to a spring, it simply won't be able to stretch further than a certain point. But if the force becomes excessive, the spring will get permanently deformed and may even break if we keep increasing the force. Hence, the spring does not remain elastic forever. This type of deformation, where the object is unable to attain, or if it only partially attains its original shape once the deforming force is removed, is called plastic. Now let me ask you a question. Suppose we have a rubber string and a string made of steel, both of very tiny thicknesses. Both are identical to each other in terms of size and shape. If we stretch them from both the ends with equal and opposite forces, then which one will stretch the farthest, assuming the deformation is elastic in both the cases? Quite obviously, the rubber string will stretch the farthest. The steel string would barely stretch, but it is important to note that it would indeed stretch no matter how little. It doesn't stretch as far as the rubber string because steel applies more resistance to the deforming force than the rubber does. Moreover, as soon as the force is removed, the steel string regains its original shape and size quicker than the rubber string. It won't allow a deforming force to change its dimension as easily. So, which one would you say is more elastic? Steel or rubber? You would think that the obvious choice has to be rubber, but unfortunately, that's incorrect. There is a general misconception that a lot of us have about elasticity. We think that the more the object gets stretched or compressed, the more elastic it is. But elasticity is not the same as flexibility. In the language of physics, the term elastic has a very different meaning. In physics, we say a body is more elastic if it resists more to the deforming force and reverses back quicker to its original shape after the force is removed. And since steel resists more and reverses back to its original shape quicker, it's more elastic than rubber. We can mathematically define elasticity as the ratio of stress to strain. We'll teach you what stress and strain mean in the upcoming videos. But get ready to be hooked to our next video on Hooke's Law.
Teddy loves tug of war. In his lifetime, he will pull hundreds of tons. That's why he needs a tailored recipe from IAMS to help him stay fit.
So we are learning only the basic things. So only the basic things. So these are all relevant to our experiment.
Many different meanings of this word. In physics, we use this word in two ways. In optics, we say a beam of light. It can be thought of as a sequence of photons traveling in a straight line. This kind of beam. Let's draw a rough general sketch of a rectangular beam. Okay, say we apply a downward force F on the surface area of a beam. Here, the force is trying to compress the beam from the top. Due to this, the beam will experience some stress. It is just an uncomfortable state experienced by the object, which is the beam in this case. The atoms inside are a little too close than they want to be. This results in interatomic and intermolecular forces, and if the applied force F is within the elastic limits of the material, these forces bring back the object to its initial state when the applied force is removed. Mathematically, stress is defined as force per unit cross-sectional area. So it is F over A, where A is this cross-sectional area. What if I increase the force from F Newton to say F plus 10 Newton on this area A? Intuitively, we know that if we push it with a greater force from above, then the beam will experience more stress. Mathematically, this new stress will be F plus 10 over A. The numerator increased and the denominator remained the same. It means that this ratio is greater than this one. So if we increase the force, the stress will also increase. Next, what will happen if I increase the surface area from A meter squared to say A plus 10 meters squared? Will the stress increase in this case too? The stress will decrease in this case because the denominator increases with the numerator remaining constant. Now, what is the SI unit of stress? Any guesses? Stress is force per unit area. The SI unit of force is Newton, denoted by N, and that of area is meter squared. So the SI unit of stress is Newton per meter squared. However, this unit is given a name and it's called Pascal, denoted by PA. Now we know the basics about stress. What is strain? In very simple language, one can define it as change in dimensions per unit of original dimensions. When any object is under stress, it will change one or more of its dimensions. The amount by which the object's dimensions will change will depend on the force applied and the materials the object is made up of. In our example, L is the length of the beam and it's experiencing some force. Hence, it will deform and its length will change by, say, delta L. Strain is defined as change in length per unit of the original length. Mathematically, it is delta L over L. So what does this ratio do? Well, the ratio compares the change in length that resulted due to force with the original length of the beam. Here, strain is calculated in terms of length of the object. But the length may not be the only quantity changing due to deformation. We can also find the strain in terms of area and volume. Let's take an example of a sponge ball of volume V. When it's compressed, its volume decreases. So the strain in terms of volume is delta V over V. Note that delta V is the change in volume and not the volume of the deformed sphere. Let's take another example where a thin rubber sheet is stretched equally from the opposite sides with a force F. And that will result in a change in the area. So the strain experienced by the rubber sheet is delta A over A. Delta A is the change in area of the sheet and A is the original area of the sheet. So in the next video, we will see the types of stress and
So these are all some of the basics actually. So these are our consideration. We have to learn about this one. So with these
shear modulus, which is also known as rigidity modulus, is almost similar to that of bulk modulus. But the difference in the bulk modulus is equal to the volume stress divided by volume strain, where the shear or rigidity modulus is shear stress divided by the shear strain. The shear modulus is denoted by capital G and it describes the material's response to shear stress. We are going to explain what is shear stress, shear strain, and how to derive the equation for rigidity modulus. Let's consider this box having length L and one side of this box is fixed. When we apply a deforming force F parallel to one of its surfaces while its opposite face is fixed, it will deform into a parallelogram. Now in this situation, the shear stress will be equal to the force divided by area, where the force is the force which acts on one of the face of this structure, and A is the area on which this force acts. So the shear stress is equal to F divided by A, or force per unit area. When we applied the force F, it displaced one of its surface, del X, from its initial position. Now the shear strain in this situation will be equal to del X divided by L. This del X is the transverse displacement caused by the force F, and L is the initial length. So the shear strain is equal to del X divided by L. This shear strain can also be denoted in terms of theta. In this triangular shape, del X is the perpendicular, L is the base, and we know that perpendicular divided by base is equal to tangent theta. So del X divided by L is equal to tan theta, and the shear strain is equal to tan theta. Now the shear modulus will be equal to shear stress divided by shear strain, where the shear stress we know is equal to force per unit area and shear strain is equal to del X divided by L. Or in terms of theta, the shear modulus will be equal to F by A divided by tangent theta. When the theta is very small, then tangent theta approaches to theta. So the shear modulus in this situation will be equals to F divided by A theta. And this is the shear modulus. which we have derived from the shear stress and the shear strain. That's it. Thank you for watching, and don't forget to subscribe his YouTube for more videos. Thank you.
Yeah, that's all, boys. So I hope you have learned something regarding rigidity modulus, the models of elasticity, elastic and plastic. If you have any doubt, you can ask your doubt. Any doubt? Adorable Sam?
No, sir.
Yeah, any doubt? Yeah, anybody? If you have doubt, you can ask. Otherwise, we can end our meeting.